Welcome to my primary maths and SATs help videos. This video is all about the main written methods for division that we learn in school today. So we'll cover words that mean division, then look at how division and subtraction are linked and how division and multiplication are linked. Then we'll look at how to use a number line to divide whole numbers, then place value to divide both whole and decimal numbers by 10 and 100 and 1000 and so on. And then we'll look at the bus stop method to divide both whole and decimal numbers. The only method I don't cover in this video is long division because in my experience it's not really necessary. So first of all, looking at words that mean division, and if we can recognise these in word problems, it can help us with knowing which calculation to use. So they include divide, share equally, split, and equal groups. And the word equal has cropped up there twice and is really important. So how are division and subtraction linked? So just as with subtraction, when we divide, we're making something smaller. So for example, if we take 12 and divide it by 2, the result is 6. And then if we take 5 and subtract 3, the result is 2. So in both cases, the answer is smaller than the original number. Also, division is the same as repeated subtraction, in other words, repeatedly taking away the same number, and I'll explain this later. Now looking at how division and multiplication are linked, when we divide, we already know that we're making something smaller. When we multiply, we make something bigger. So we say that division and multiplication are inverse or opposite operations. And please have a look at my video on multiplication if you would like more information on how we do that. So we're going to start by looking at how to use a number line to divide, and this is where the concept of division being the same as repeated subtraction comes in. In other words, taking away the same number or group each time. So here's an example. Now the thing I always think makes division difficult is the fact that we can read division calculations in different ways, and it will depend on the question which way we read it. So if we look at this one, we could read this as 15 divided by 5, or 15 shared into 5s, in other words, groups of 5, or 15 shared between 5. So if we take the second of these to start with, I'm going to draw a number line, and what we're going to do is we're going to put the 15 at the right hand end. In other words, the number that's going to be divided, we call that the dividend, goes at the right hand end, and at the left hand end we put a 0. And what we're going to do is take away groups of 5 and see how many of them there are. So if we start with 15, we take 5 away from 15, we reach 10. And if you're using a number line, you must always remember to write the number that you reach as you go along underneath the line. So that's one group. Now, can we take 5 away from 10? Yes, we can. That will take us to 5. That's a second group of 5. So we've got 5. We take the last 5 away, we reach the 0. And there we have 3 groups of 5. So we've shared the 15 into 5s, and there are 3 groups of them, equal groups. And that's our final answer. I can demonstrate this in a slightly different way. So if we have our 15, we're going to share it into 5s again. 5, 10, 15. So there we have the 3 equal groups. And by showing it like this, you can see the very close link between multiplication and division, because I've just used my 5 times table to count up to the 15. Now, if we look at the third way of reading that calculation, which is 15 shared between 5, let's do that now. So imagine we've got 15 sweets. We're going to share them equally between 5 friends. If I think about my 3 times table, 3, 6, 9, 12, 15. There we have. Each person is going to get 3 sweets. Now let's look at a second example. So again, we could read this in different ways, including these 3 ways. So 24 divided by 6, or 24 shared into sixes, in other words, equal groups of 6, or 24 shared between 6. So if we take the second one again, we do as we did before. We draw our number line, we put the dividend, the 24, the right-hand end, and a 0 at the start. And then we're going to take away, this time, groups of 6 and see how many there are. So 24 subtract 6 takes us to 18. That's our one group. We can definitely take another 6 away from 18, which will take us to 12. And we can take a 6 away from 12, which takes us to 6. So that's the third group. And then if we take the final 6 away, that'll take us to the 0. So there we've got 4 equal groups of 6. Again, if I demonstrate this way, 24 shared into sixes, we can see that there are 4 of them, 6, 12, 18, 24. So I'm using my 6 times table to check. And then if we look at the third way of reading that calculation, 24 shared between 6. So perhaps there are 24 pieces of pizza and we share them between 6 people. How many pieces are they each going to get? And there, if we count up in our 4 times table, that will make 24. So each person has 4 pieces of pizza. Now, using a number line is very useful for demonstrating what division means, this idea of sharing into equal groups. But as a written method, we don't generally use it a great deal. So now we're going to look at the place value method, and it's essential that we use this method whenever we're asked to divide any number by a 10 or 100 or 1,000 or 1,000,000, in other words, by a power of 10. So I've got our place value scale here, and if you need more information on this, please do look at my video on place value. And we've got our first example here. So we've got 341 divided by 10. Now, before we start, we just need to remind ourselves that when we're dividing, the answer will be smaller. So if we're thinking about our place value scale, the numbers get smaller the further towards the right that they move. So if we put the 341 on there, now let's look at what happens when it's divided by 10. So the digits are identical, but what's happened is each one of those has moved 1 place to the right. So the answer is 34.1. And we don't have to worry about the decimal point being in the way. We simply just move the digits to the next column along. Let's look at another example. This time 34 divided by 10. And again, each digit has just moved 1 place to the right. So 34 divided by 10 is 3.4. Let's look at the last example. This time 3 divided by 10. And people's reaction is quite often, well, I can't do that. But yes, you can divide by a bigger number. And the place value scale really helps when we're dividing by 10 or 100 or 1,000. So if we put the 3 on the scale, thinking about the pattern, the 3's move 1 place to the right, and then we have to remember to put our placeholder in. So the answer is 0.13. So there's a tip here, and that is a 10 has got 1 0. So if we're dividing by 10, we move the digits 1 place to the right. So 1 0, 1 place to the right. And there's something else to note here, that when we divide by 10, the answer will be 10 times smaller than the original number. So if we look at the first one, 34.1 is 10 times smaller than 341. So let's now see what happens when we divide a number by 100. So here we've got 24 divided by 100. So we've got it on the scale. Let's see what happens. So again, the digits are exactly the same, but they've moved 2 places to the right, and then of course we've had to put our placeholder in before the decimal point. So the answer is 0.24. Let's have a look at another one. So 543 divided by 100. Again, we've got the same digits and they've moved 2 places to the right again. So the answer is 5.43. So again, there's a tip here. 100 has got 2 zeros, so that reminds us to move the digits 2 places to the right. 2 zeros means 2 places. Now let's look at what happens when we divide a number by 1,000. So we've got 17 here. So this time the digits have moved 3 places to the right, and then we've had to put placeholders in the tenths column and the units column. So the answer is 0.017. Let's look at the last one. And this time again dividing by 1,000. And once again, all of the digits have moved 3 places to the right. So the answer is 8.690. Now, we don't actually need to keep the 0 at the end because a 0 at the end of a decimal number has no value. So actually we could say that the answer is 8.69. Leaving the 0 on is not a problem. And here, hopefully we can see that 1,000 has got 3 zeros and we've moved the digits 3 places to the right. So 3 zeros, 3 places. So if we follow the same pattern, if we were to divide a number by 10,000, which has got 4 zeros, we would move the digits 4 places to the right, remembering of course to put any placeholders in. If we were to divide by 100,000, we would move the digits 5 places to the right, and if we were to divide by 1,000,000, we would move the number 6 places to the right because 1,000,000 has got 6 zeros. And once again, we need to be aware of the fact that when we're dividing by 100, we're making a number 100 times smaller, and when we divide by 1,000, we're making a number 1,000 times smaller. So far, we've looked at what happens to whole numbers when they're divided by these powers of 10. Now let's look at what happens with decimal numbers. So here we've got 3.7 divided by 10, and this is what happens. Once again, exactly the same, both of those digits have moved 1 place to the right, so 10 has got 1 0, so 1 place to the right, but then we've had to remember to put our placeholder in before the decimal point. So the answer is 0.37, and 0.37 is 10 times smaller than 3.7. Another example. Once again, all of those digits have moved 1 place to the right, so the answer is 50.671. And it's really important that if there are any zeros in the number, that those move as well. Now we've got a decimal number divided by 100. And just as before, 100 has got 2 zeros, so we move all of those digits 2 places to the right, and then we've had to remember to put our placeholders in the tenths and the units column. So the answer is 0.083, which is 100 times smaller than 8.3. And one more example, 94.2 divided by 100. Again, all of those digits move 2 places to the right, and then we've put a placeholder in before the decimal point, and there's our answer. There's just one more thing to say here. It's really important that we only use this method if we're dividing by one of these powers of 10. So you would not use it if those numbers are swapped around. For example, 100 divided by 43 is not the same as 43 divided by 100, so we need to look out for that. Now we're going to move on to what's known as the bus stop method for division, and this is the one we generally use unless, of course, we're dividing by one of those powers of 10. And we're going to focus first on whole numbers. Here's our first example. And again, we need to be aware that we can read this in different ways depending on the context. The first thing we do is draw our bus stop. The big number to be divided goes inside it. The smaller number outside and to the left. And the bigger number, as we've heard before, is known as the dividend. The smaller number is called the divisor. And now we're going to see how closely linked multiplication and division are. Because what we need to do in order to solve this problem is to know the times table of the divisor, in this case the 7 times table. So what I always say is if we don't know that really well, it's a good idea to write out at least the first part of it down the side of the page. You only need to write out as much as you need for the calculation. So I've done that here, and what I'm interested in are the answers, the products. So I've circled those in red, and the way I like to read the times table is this: 1 times 7 makes 7, 2 sevens make 14. So if we look at our bus stop now, we're going to say to ourselves, how many 7s make that first 2 in the 245? The answer is 0, because if we look at the 7 times table, we can't make 2. The smallest number we can make is 7. So we put a 0 above the 2 and the bus stop, and it's really important that we line up our digits really carefully. So 0 times 7 makes 0, but we needed to make 2. So we cross off the 2 that we didn't make and we pass it across to the next column. We then read that number as 24. Now we look down our times table. Can we make 24? No, we can't. So what we do is we look for how close can we get to that number without going over it. Well, we can get to 21, and 3 lots of 7 make 21. So I'm going to take that 3. I write it above the 24 on the bus stop. So 3 7s make 21, but I needed to make 24. So there's a difference there of 3. There are 3 left that we didn't make. So if you do 24, subtract the 21, you're left with 3. So then what I do is I cross off the 24 and I pass the 3 across that I didn't make to the next column. And I do think it's useful to do the crossing off as you go along, and then you don't lose track of where you are. I then read that number as 35 and I say, how many 7s make 35? Can we make 35 in the 7 times table? Yes, we can. And it's 5 lots of 7 make 35. So I take the 5 and I write it above my bus stop. And there's my answer. So if I'm looking at the way we can read that calculation, if we look at the second way, which is 245 shared into 7s, in other words, into groups with 7 in, there would be 35 groups. If I look at the third way of reading the calculation, so 245 shared between 7, imagine 7 friends, each one of those would get 35 of whatever it is we're talking about. And just as a reminder, I do think using this language is really useful. How many 7s, or whatever the divisor is, make. So let's look at another example. Here we've got 367 divided by 5, but again we could read that in different ways depending on the question. We draw our bus stop, the dividend goes inside, the divisor on the outside, and this time we're going to need to know our 5 times table. So I've written part of it out here. Again, we're looking at the answers, the products that we make, and reading them as 1 times 5 makes 5, 2 5s make 10, and so on. So we look at our bus stop. Step 1 is we say how many 5s make the first 3. The answer is 0 because the smallest number we can make in the 5 times table is 5. So we put 0 above. 0 times 5 is 0. We needed to make 3. So again, we cross off the 3 and we're going to pass the whole digit across to the next column. We then read that as how many 5s make 36. Looking at the 5 times table, the closest we can get to without going over is 35, and that's 7 lots of 5. So we write 7 above 36 on the bus stop. 7 5s are 35. We needed to make 36. There was one left that we didn't make. So we cross that off and pass the remainder across there. So then we read that as 17. How many 5s make 17? Again, we can't do that in the 5 times table. The closest we can get without going over is 15, and that's 3 lots of 5. So we write the 3 above the bus stop there. Now, basically, we've finished the calculation, but we know that we were asked to make 17. We only made 15, so we've got 2 left over. So what we have to do is then write that as a remainder 2. Now, it depends on the type of question that you're answering, whether it would make sense to have a remainder, and that's something that you have to work out when you're solving word problems. And just as a reminder, it's important to realise that the remainder is what's left over from the dividend, so in this case, the 367. So we would write our final answer like this: 73, small r for remainder, and then 2. So if we're looking at the different ways of reading that calculation, if we look at the second one, 367 shared into 5s, in other words, groups with 5 in them, we would have 73 whole groups with 5 in and then 2 items left over. Or if we were looking at the third way of reading the question, 367 shared between 5, so imagine between 5 people, for example, each one of those people would get 73 of whatever it is, and then there would be 2 items left over at the end. So we've looked at how to use the bus stop method when we have a single digit divisor. Now let's look at what happens when we have a 2-digit divisor. Here's an example, and again we can read this in different ways. Just as before we draw a bus stop, we put the dividend inside, the divisor to the left on the outside. So now we're going to have to focus on our 13 times table to solve this problem. So I've written part of it out here, and just as before, we're interested in the products, the answers that we can make. Just as before, we start by saying how many 13s make the 5. The answer is 0. The smallest number we can make is 13, looking at the times table. So we put 0 above. 0 times 13 is 0. We needed to make 5. So we cross off the 5 and pass the whole digit across to the next column along. We read that as 54. How many 13s make 54? Looking at the 13 times table, the closest we can get without going over is 52. And that's 4 lots of 13. So we write the 4 above the 54 on the bus stop. We only made 52, we needed to make 54, so there are 2 left over that we didn't make. Cross that off, pass the 2 across, and read that as 29. How many 13s make 29? Again, we can't do that. Closest we can get is 26, and that's 2 lots of 13, so we write 2 above. So just as before, we needed to make 29, we only made 26, so this time we've got a remainder of 3. And as before, that's what's left over from the dividend, in this case the 549. So that's our answer. So if we're looking at different ways of reading that calculation, if we had read it as 549 shared into 13s, groups with 13 in them, there would be 42 whole groups and then 3 items left over. If we had read it as 549 shared between 13, say 13 people, each one of those would get 42 and there would be 3 items left over. So there's absolutely no difference in the method between calculations that have 2-digit or single-digit divisors. The method is identical. Now we're going to look at a slightly different problem, again using whole numbers, but I want you to imagine a real-life scenario here. So for example, there is a race 806 kilometres long. We've got 16 runners and we want each of those runners to run exactly the same distance. So this is an example of a division problem where it would make absolutely no sense to have a remainder answer, because the remainder would be kilometres left over, and we can't have that because they've got to run the whole race. So this is what we would do. We set out the calculation exactly as we did before. This time we need the 16 times table. And then we carry on just as we did. So how many 16s make 8? 0. We cross off the 8 and we pass the whole digit across. Then how many 16s make 80? We can make 80, and that's 5 lots of 16. We then cross off the 80. There's nothing to pass over. Then how many 16s make 6? The answer is 0. So we've just said we can't have a remainder answer, and we know that the calculation isn't finished because we've got those 6 that we didn't make. So this is what we have to do. First of all, we have to recognise that although we don't put them in, whole numbers do have decimal points after them. So that's what we do first. We have to put in those decimal points going immediately after the units column. If we think about our place value, making sure that we line them up one above the other. And then what we do, we need to continue the calculation. So we put a placeholder in the dividend inside the bus stop. And now what we can do is we can pass the 6 across that were remaining over to there. And then we simply read that as 60. We don't have to worry about the fact that it's 60 tenths because the calculation has got the decimal points in, it knows the value of the digit. So we can just in our head say 60. How many 16s make 60? The closest I can get is 48, which is 3 lots of 16. We still haven't finished the calculation. So what I do is I put another placeholder in so that I can carry the remainder, cross off the 60 and pass across the 12 that were left over. And now I can read that as 120. How many 16s make 120? Again, I can't make that. The closest I can get is 112, which is 7. And we still haven't finished. And because we're talking about kilometres, it does make sense to have those thousandths. So I'm going to put another placeholder in. I cross off my 120 and pass across the 8 remainder. And now I can read that as 80. How many 16s make 80? And we can do that. It's 5. And that's the end of the calculation. So that is my answer. So I've just mentioned about the kilometres. Now some calculations could carry on beyond the thousandths column, but in real life this would rarely make any sense. And in some cases, for example, metres or something like that, it would only make sense to have tenths or hundredths as the final digit. So ideally, and to be as accurate as possible, it's usually best to calculate one more digit than is needed if the calculation isn't finished, and then round the answer. So if you need some help with how to do rounding, please do have a look at my video on estimating and rounding for a bit of help on that. So far we've looked at how to use the bus stop method with whole numbers. Now we're going to look at how to use it with decimal numbers. Here's our first example, different ways of reading it, and this is how we set it out. The dividend goes inside, divisor there, so we're looking at the 4 times table this time. We're interested in the answers or the products. And this is what we have to do. This is linked really with the last slide that we've looked at. The first thing we have to do when we're dividing a decimal is to put the decimal point in our answer first. Absolutely crucial, and again it has to be lined up exactly with the decimal point in the dividend. And once we've done that, we simply carry on exactly as before. So how many 4s make 9? Closest I can get is 8, which is 2 4s. So there's 1 left over, which we pass across. How many 4s make 13? The closest I can get is 12, which is 3 4s. Again, there's 1 left over, so I cross off the 13. And just as I've shown in the previous slide, we simply pass the 1 across to there. And again, we don't have to worry about the value of the digits. The calculation knows. So we read that as 16. How many 4s make 16? The answer is 4. Nothing left over. How many 4s make 8? The answer is 2. And there's nothing left over. So there's our answer. So we might have another real life scenario. This time perhaps there's a length of fabric of 93.68 metres long, needs to be split up or divided up into 4 equal pieces. Each piece would be 23.42 metres long, nothing left over. Here's another example, but this time it's going to be slightly different. So different ways of reading it. We set it out exactly as before. This time we need the 6 times table. And again, the next important step is to put our decimal point in our answer first, lined up carefully with the other one, and then off we go. How many 6s make 4? 0. Pass the whole 4 across. How many 6s make 46? The closest we can get is 42, which is 7 6s. Cross the 46 off, pass the 4 that we didn't make across. How many 6s make 48? We can do that. That's 8 6s. Nothing left over. Then we simply jump to the 7. So how many 6s make 7? Closest we can get is 6. So one lot of 6 is 6. And then we've got 1 left over. So how many 6s make 15? The closest we can get is 12, which is 2 lots of 6. Now, we cannot have a remainder answer if we're dividing a decimal. Because if we say, for example, here we would have remainder 3, because we only made 12 and we needed to make 15. If we say remainder 3, that means 3 whole digits. And it can't be, because we're already, if we think about our place value, we're talking about 3 hundredths. So we cannot have remainder answers with decimal numbers. So just as we did with that whole number where we had the kilometre scenario, the race, we have to extend the calculation. So what we do, just as before, we put a placeholder in the dividend and we continue with the calculation. So the last part was how many 16s make 15, so how many 6s make 15? The closest we could get was 2 6s to make 12. So 3 left over, cross the 15 off and pass the 3 across. And then we read that as how many 6s make 30, and that's 5 6s make 30, and that's the end of the calculation, nothing left. So there's our answer. So just as before, if we need to continue the calculation, we simply add placeholders one at a time and then continue carrying any remainders as before. Always thinking about the unit of measure that we're talking about. Does it make sense to have an answer with hundredths or thousandths or just tenths? So here's a summary of the bus stop method. Think about the question, will a remainder or a decimal answer make the best sense? How many decimal digits would make the best sense? And this will depend on the unit of measure, so meters, centimetres, litres, grams, etc. Set out the bus stop with the large number or the dividend on the inside and the small number or divisor on the outside. Write out the divisors times table, just the first half to begin with to refer to if you need to. Use the language, how many those make those. I think it's really useful to do that. Carry any leftover amounts from the dividend to the next column. And if necessary, add a decimal point to the dividend and the answer before continuing. When you're dividing decimals, you do exactly as above, but make sure you put the decimal point into the answer first. And if necessary, add placeholders to continue the calculation. Consider whether the answer needs to be rounded, and this will depend on the context of the calculation. And again, we should always estimate first and check our answers against the estimate. So if you need help with that, please have a look at my video on estimating and rounding. Here's a practice page in case you'd like to have a go at some on your own. As you can see, I've put down whether the answers need to have remainders or be decimal answers. And if they're decimals, that means you might need to use those placeholders to extend the calculation. You don't need to worry about any units of measure. And you may just want to pause the video at this point so that the answers don't come up too quickly. So the answer to number 1 is 23. Number 2, 40 remainder 7. Number 3 is 40.75. Number 4, 57 remainder 5. Number 5, 32.25. And number 6, 81.18. I do hope you found this video useful, and if you have, please do have a look at my other primary maths and stats help videos. Thank you for watching.